Okay, hi class, how are you? This is Ian. Remember me, I'm your chemistry teacher. And we're just going to go over week 11, but before we do that, I hope you guys are doing well and you guys are safe and y'all are washing your hands. Sing a little song for 20 seconds, that's what they say. And keep 2 meters away from people, social distancing. And again, I hope all of you guys are doing awesome and at home with your families. And as long as you guys stay well and healthy, this could be a nice opportunity and good family time. Both my kids have been at home and my wife's been at home, and we've just been enjoying some good time. And keep up on your stuff. I'll be in constant contact, and get out of here with some good marks and move on. So in order to do that, this is used to be my week 10. You might see that reference throughout the PowerPoint, but this is the new week 11. And we'll make this as painless as possible. Everything here is on your assignment that's out there, so let me know if you're having any issues. But other than that, let's get rocking and rolling. Week 11, alcohols, ethers, and phenols. Basically, this is about water, because you're going to see here on the next slide all the things we're going to cover there. It's about phenols, alcohols, ethers, but really what we're talking about here is the structure of water. And you'll know there that if you look down here, this is remember the R group is a bunch of carbon, 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 carbon. Could be 1, could be 10, 20 carbons, okay? But this is the shape of water. H2O right here. And water is polar, as you know, okay? Here we've got a phenol, okay, which is a benzene ring, and you'll know there that this is absolutely 100% non-polar, right? It's just carbon and hydrogen. There's no big side, polar side to it. That this is non-polar, and then all of a sudden you have this polar branch off the end. Okay, going back to an yeah, it's 10:30 at night. Aliphatic carbon chain group here with an alcohol group. This would be non-polar, but you have this polar end to it. And we'll get into more of the structure and function of these guys here. But here, let's move on. Alcohols, ethers, and phenols. Here's your water shape. Here's your alcohol. Okay, aliphatic carbon chain. Okay, an ether. Okay, this is a carbon chain on this side. There's a carbon chain on this side, but then you have this oxygen in the middle. And remember, oxygen is one of the most electronegative elements out there. It likes to steal electrons. So if you see an oxygen, generally you're looking at polar molecule. And remember, when it comes to polarity and making solutions and these kinds of things, polar likes polar. That's why ethanol, okay, that should make sense to you by now, goes into water. Because water's polar, ethanol has an alcohol group on it, and it is polar. Polar goes into polar. Ethers, though, you're going to see something a little different, all right? But they're slightly polar. And then you have phenols over here. It's almost, you have these opposing agents. Here you have a polar alcohol group, hydroxyl group, and you have a non-polar benzene group here. Alcohols are classified by the number of R groups attached. Now, we've gone through this. We did this there, it seems like a million years ago, but we did this already. Remember a primary alcohol, okay, where the hydroxyl group is attached to a carbon that is only attached to one other carbon. A secondary alcohol is a hydroxyl group attached to a carbon that is attached to two other carbons. A tertiary alcohol is a hydroxyl group that is attached to a carbon that attaches to three other carbons. Their chemistries will be a little different. Different types of structural formulas of 2-butanol. And you just look at this here. But means 4 carbon. All means an alcohol group. 2 refers to where the alcohol group is. It's coming off the 2 carbon. So you have here 1 carbon, 2, 3, 4. That's a but. Here I have an alcohol, butanol, 1, 2. It's coming off the 2. Here is my structural or condensed structure, or sorry, my structural formula here, and here's a condensed structural formula here. Okay, all are fair game. And if you, the most difficult one here is the condensed structural formula. Okay, like you look at this. Okay, there's an alcohol group, but where is it coming off of? You remember your terminal carbons will always be CH3. Carbon has 4 bonds, so there's a hydrogen, 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 and this carbon here is attached to this carbon. And interior carbons will be CH2. But you look at this one here, CH. Wait a second, that carbon is missing something here, so therefore this alcohol group must be coming off of here, so that's why it's 2-butanol. Where when we get into sugars here, they can be written like this. Okay, alcohols with more than one hydroxyl group. Okay, you look at galactose, look at glucose. Okay, glucose can be written in a ring structure, but it can also be written like this. Okay, regardless of whether it's written in a ring structure or a straight line chain, you'll see there we call it a polyhydroxyl alcohol. Interesting, eh? Each hydroxyl group in a polyhydroxyl alcohol can be classified as primary, secondary, or tertiary. Classify each hydroxyl group in D-galactose. So, how would you do this? You look at this alcohol group right here. It's attached to a carbon that is attached to 2 other carbons. Here's another alcohol group that's attached to a carbon that's attached to 2 other carbons. And so on and so forth. You look at this alcohol group. It's attached to a carbon that is only attached to 1 carbon. Okay, so you should be able to tell that we've got a primary and then we've got secondary alcohols throughout. Little bit of what is this guy called? This is a aldehyde. Just for a little bit of knowledge there. And there we go. All right, secondary, 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 single, primary. Yeah. All right. Oh, and by the way, if I'm going too fast, you can just rewind it. Yeah. See how the following examples are named. Okay. This is very, very important. Okay. You have to make this make sense. And you remember that very first in the I think week 8, the blue slide there that had meth, eth, prop, but, pent, you know, pentene, and had ine and all that. That still carries weight here, and like I said, that's the most important slide of the entire semester or half semester. Okay, you gotta know the number of carbons and the name. 3 carbons here is prop. Okay, now it's propanol. All means alcohol. Now it's 1 propanol. Now remember, if you're going to put a 1, there had better be a 2 out there somewhere. All right, and because see, this alcohol group could be coming off of here, which would mean 2-propanol, as in this case right here. Here we've got, this is not benzene. Trust me, you'll see this on the final, even on the assignment. This is not benzene because there's no ring in the middle. This is cyclohexane, okay, and this is cyclohexanol. It's not 1 cyclohexanol, because if I take this alcohol and put it here, that could still be counted as number 1. I could put it over here, and this carbon here could still be number 1. In this case here, I've got 1,3-cyclohexanediol. Make it make sense. Everything there should. 1,3-cyclohexanediol. Okay? And just to note, we don't use ortho, meta, para for cyclohexane. We only use ortho, meta, and para for benzene. Okay? This one here, you're trying to figure out what's going on. Find my longest chain. 1, 2, 3, 4. So that's a bute. There's no doubles or trips. All right, so it's butanol. And where do I start numbering from? Well, you always start numbering from the big banana here. Which is the biggest here? Well, I have an alcohol group here, but I have a methyl group here. The alcohol group will trump the methyl group, so you start counting from here. 1, 2, 3, 4. So it'll be 3-methyl, 1-butanol. And have a look here. What's my longest carbon chain? I have 1, 2, so that'll be an ethane. Okay, an ethane. And I have an alcohol group here. I have an alcohol group here. So that'll be 1,2-ethanediol. Now, look at this example here. What if I had 2 alcohol groups on the same carbon? And not 1 over here. It would be 1,1-ethanediol. Okay? Try it again. Go over this one. This is a good one. I would know this one inside and out. Okay? Name the following alcohol using the IUPAC method. Again, 1, 2, 3, 4, 5, 6, 7. Okay, that probably looks like heptane. All right. And it looks like I've got a methyl group here and a methyl group here, and I've got an alcohol group here. So the alcohol group would trump. So I got a name, I got a number from this side. 1, 2, 3. So it would be 3-heptanol. And then 4, 5, 5, 5 dimethyl heptanol, as best as I can see. Okay, good. Write the structural formula of 2,4-dimethyl 2-hexanol. All right, 2,4-dimethyl 2-hexanol. How would you recognize? Now, you're not going to have to draw this on your assignment or your test. You're going to have to be able to recognize it out of a crowd of 4. All right. How do you do this? Start from the back side. Okay, so I got hexanol. I got 2-hexanol. So you're going to have space to draw this there on your test, so don't worry. So you draw your 6-carbon chain with an alcohol group coming off of the 2-carbon. There's your 2-hexanol. Always start from the back side, work your way forward. I got dimethyl. Okay, 2,4 coming off of that one right there, and there you go. All right, so physical properties of alcohols, as we said, they are polar. Okay. Hydrogen bonding. Okay. That's why ethanol goes readily into water. There's lots of hydrogen bonding going on here, which is what's going on right here. These instantaneous bonds that are created and dissipate in a millionth of a second, but allows water to act like cement. Increase in boiling points of alcohols compared to the corresponding alkanes. Okay, so if you have an ethane and ethanol, the ethanol will have a higher boiling point because the molecules are more strongly bonded together because of hydrogen bonding. So therefore it'll take more energy to break them apart, which means the boiling points will be higher. Increased solubility of alcohols in water as compared to corresponding alkanes. So if you look at butane and butanol, butane ain't going into water. It's nonpolar. 4-carbon chain, absolutely nonpolar, but butanol will go into water because of the alcohol polar group on the end. Just some reference points here. You'll see there that as you increase carbons of like pentane, hexane, octane, decane, the boiling point does increase because you got more carbons, bigger molecules. But if you have a look at the pentanol, hexanol, octanol, decanol, their boiling points also increase because the molecule is getting bigger. But let's look crossways. Pentane, boiling point 36 degrees. Pentanol, big jump. It's all because of that oxygen. It's creating polar bonds and hydrogen bonds and these kinds of things. List the alcohols below in order of increasing boiling point. So how would you answer this one? Go for your smallest one and go up. So there's your methanol, prop, bute, pent. Okay. Stupid mouse, not working. We have seen this there before. This is a bit of review. Guarantee it, you will see it again. Oxidation of alcohols. If you have a primary alcohol and you oxidize it, what do I mean oxidize? Adding oxygen. If you have a primary alcohol, you can oxidize it once and you will create an aldehyde. You can keep oxidizing primary alcohols to the end point, which is a carboxylic acid, and the reaction will stop. Primary alcohols can jump to aldehydes, which can jump to carboxylic acids. Why can they do this? Because they're on a terminal carbon. Secondary alcohols, okay, which is a carbon attached to two other carbons. And you can see how an aldehyde here and a ketone are related. An aldehyde basically is a ketone, but it's on the end. That's why this first reaction can keep going. But a secondary alcohol, it can be oxidized into a ketone and then it stops. Okay. A tertiary alcohol, no, will not be oxidized. That's it. It stays a tertiary alcohol. Okay, and just on a test there, if you see some common oxidizing aid, just look for the oxygen. Okay, ding ding ding. If you see an alcohol plus something sitting on the arrow like this, an oxygen, or something full of oxygen right here, this is what I'm looking for. I'm going to be looking for one of these, or one of these. And basically you have to be able to tell. What I'm asking is it a primary, secondary, tertiary alcohol? And if I add oxygen to it, what is going to be my end reaction? This whole process is used in breathalyzers, by the way. An application of the oxidation of alcohols is used in the alcohol breath analyzer test. Okay, the color change in the ethanol dichromate reaction is used in alcohol breathalyzers. That's how they tell if you got alcohol on the breath. Metabolism of ethanol. Ethanol is oxidized in the liver to produce ethanal. Okay, ethanol is oxidized in the liver, which produces ethanal. Aldehydes, al. Excess alcohol consumption can cause cirrhosis of the liver. Ethanal is oxidized to acetic acid. So you see here, this is a primary alcohol. It's oxidized to the aldehyde, which is then further oxidized. Continues down here. There's my ethanal, old school name, acetaldehyde. Ethanal is oxidized to acetic acid, vinegar. Okay. Acetic acid is actually a source of biochemical energy and thus contributes to overall calorie intake. Okay, your body can break this down. There's lots of energy in that. What are the products when 2-butanol is oxidized, okay, and heated? So 2-butanol. Question I'm asking, you're going to have to draw it out. Is it primary, secondary, tertiary? There it is right there. So you look at that. That carbon right there is secondary, and it's in the middle there. Okay, so therefore now you're looking at a ketone. Okay, butanone. Good little question is, why isn't that called 2-butanone? See if you can figure that one out. It's not. It's just butanone. And by the way, can there be a 1-butanone? What do we got now next? Dehydration reactions. Alcohols are dehydrated to form alkenes. We've seen this there before as well. Okay. So there's your alcohol right there. If we put some sulfuric acid in it, okay, what happens is the sulfuric acid adds a hydrogen to this guy right here, all right, and it floods there with hydrogen. So therefore now this guy right here, though this water comes off and one of these bonds flips up, which creates the alkene. Dehydration, ethers. Remember ethers, where you have a carbon chain bonded to an oxygen, which is then bonded to another carbon chain. Ethers can be prepared by a dehydration reaction between two primary alcohols. Okay? Reaction in which two molecules combine by removing a small molecule is known as a condensation reaction. So what we have here is, you have a look. Here I have ethanol, which is a primary alcohol. Here I have another molecule of ethanol. And what happens is, again in the presence of H2SO4, water is sucked out. But it still leaves an oxygen here, and this guy here flips up here, which produces, okay, old school name, diethyl ether. We'll get to the new name there, okay, diethyl ether, but we'll get there. That's not the name I want you guys to know. What ether is formed from two molecules of 2-butanol? Okay, so here I have 2-butanol. You can just see what's going to happen here, and that's what this test and the assignment's all about, is just getting you to recognize here what's going to happen. Here I have two alcohol molecules, and I have H2SO4, which is flooding it there with hydrogen, and what's going to happen is here is we're going to make an ether. That's it right there. Okay. Esterification. This is another this is a relative of the carboxylic acid, okay, and it's a relative of amino acid formation, but it's actually called the amide, but we'll get there as well. Alcohols react with carboxylic acids to form esters. So here I have a carboxylic acid, okay, and here I have a alcohol. What happens is, again, in the presence of H2SO4 or an acid, of strong acid, what's going to happen here is we're sucking out of water, which now makes an ester. All right, which correlates there to your current lab number 5. Okay, here I have acetic acid. Okay, or IUPAC name, ethanoic acid, just vinegar, ethanoic acid, plus ethanol. Okay, and this is how we name esters. Here we've got ethyl acetate, okay, and water here. 3 important reactions involving the hydroxyl functional group, and this is what I need you guys to know. Okay, here we've got oxidation, primary, secondary, tertiary. Will produce these guys here. There's a dehydration reaction, which is in the presence of hydrogen. That will make alkenes and ethers. Okay, how do I make an ether? 2 alcohols. Okay, how do I make an ester? That's a carboxylic acid and an alcohol. Properties and applications of methanol. Boiling point is 65 degrees Celsius. Okay. Poisonous and can cause blindness or death. You know, they've that's in windshield washer fluid, these kinds of things, and bad stuff. Application, feedstock to produce the intermittent formaldehyde. Okay. Industrial solvent, denature, and for ethanol. Okay. How do we prepare ethanol? Ethanol can be prepared by the acid catalyst addition of water to ethylene. Okay, we would just call the new school name there is ethene, but here we have an ethene molecule plus water in the presence of hydrogen. What happens is we flood this double bond, we attack the double bond, and an OH goes on one end and a hydrogen goes on the other, which produces ethanol. Okay. Properties of ethanol: boiling point of 78 degrees. That's how, if you've ever noticed there, how they make spirits from all types of spirits, alcohol higher than 20%, or they're made by, all of them are made by fermentation processes. And then to get the alcohol content up, what they do is they gently warm this fermented mash, and the alcohol, which boils at 78 degrees, okay, comes up, I guess, through the copper tubing and then comes out the other side, and that's your high percentage of alcohol, and the water ends up staying in the original bucket. So you see the boiling point there is significantly lower than water. Okay, here's a good word here, hygroscopic. 100% ethanol takes up water very quickly until a stable concentration of 95.6 ethanol is reached. Good little word there. Applications, depending on the quality consumed: food, drug, or poison. Commercially used as an intermediate in the manufacture of other chemicals such as acetic acid, okay, ethanol, ethanol, used as a solvent, okay, perfumes, flavorings, it's all over the place, okay. Preparation of 2-propanol. 2-propanol, also called isopropyl alcohol, rubbing alcohol, which you guys should all have jugs of it at home right now, okay. And by the way, if you run out of hand sanitizer, okay, which I was in Canadian Tire there a week ago, and these little, I don't know, man, it must have been 100, maybe 200 milliliters. Basically the size of a small milk carton you get back in grade 5. And they were going for $7.99. Just a complete scam. Go to Walmart or go anywhere and go and get a big jug of isopropyl alcohol for like $1. Okay? And you fill your little squeegee bottle or something up, and you just carry that around with you. Okay, if you got to go into Zehrs, you just spray the cart down and all that kind of stuff. Don't go and buy the expensive stuff. Just go for the cheap stuff. The isopropyl alcohol, rubbing alcohol, 2-propanol will work just fine. And 2-propanol is a secondary alcohol prepared from propene. And it's the same reaction as before. You see here we have a propene. If we add a hydrogen and water to it, this thing is going to attack the double bond and break it and make it 2-propanol. Applications of 2-propanol. Here we've got manufacture of chemicals like acetone, nail polish remover. Okay. Here we have 2-propanol. Now, let's go back to this. Here I have 2-propanol. This is a secondary alcohol. This carbon is attached to 2 other carbons. If we oxidize it, the only thing we're going to get is a ketone, and the reaction will stop. All right. It's also an industrial solvent and rubbing alcohol, of course. All right. Now, where are we? Good. We're moving along. Applications of ethylene glycol. The IUPAC name there. Ethane 1,2-diol. Ethane, 2 carbons, 1,2-diol. Okay. Manufacture of polyester fibers, manufacture of explosives, funny enough, antifreeze, ethylene glycol, used as solvent for paints, plastics, and inks. Okay, here are some more properties here. 1,2,3-propantriol. Okay, there's lots of things there that these guys are used for, usually in the polymer and explosive industry. Here we've got nitroglycerin, okay, which is basically just a precursor of the above there. Okay. Getting into phenols, and I received a couple of emails there. People are having difficulty with naming benzene groups, and yeah, you know what I mean. That's why I put that extra, was it 2 or 3 or 4 pages of how to name benzene derivatives, because some of them, most of them go by some type of IUPAC name, but there are some there like phenol, which is just phenol. There's no other name for it. Okay. It's an organic compound that has a hydroxyl group attached to aromatic ring. Okay. And this is it right here. So it's a benzene with an alcohol group, and just phenol right here. There is no 1 phenol. There's no 2. That's it. There can be a 1,2 or a 1,3, but if it's just a single hydroxyl group on it, no. Naming of phenols, again, with benzenes, we can use the ortho meta para, or you can also use numbers as well. This one here I've got the benzene group, I've got an alcohol group, and I've got a bromine group. I got 2 functional groups on this one. Which trumps which? The alcohol trumps it all. So this is phenol. So this will be M-bromophenol. Ortho, meta, and then para, remember, is on the opposite sides. Here I've got p-aminophenol. And if you look at this one here I've got my phenol group. I've got a nitro, 2,4,6 trinitrophenol. Why is it 2,4,6? Because this guy here is always number 1. Name the following phenol derivatives. I've just put these here for you. There's my phenol group. 2, 3, 4, 5 dibromophenol. Here I've got p-ethylphenol, para-ethylphenol. And here's my alcohol group here. So this is number 1, 2, 3, 4. 4-chloral, 3-nitrophenol. Why did I go 4 and then 3? Because that one there, alphabetical over N. See, same rules as before. Some phenol derivatives are used as flavoring agents. Here's vanilla, eugenol, I don't know, Google that one there. There's your cloves, and thyme. The toxicity of phenols to microorganisms makes them excellent antiseptics. For example, 4-hexyl-1,3-benzenediol is used as an antiseptic in many pharmaceutical preparations. Phenols occur naturally in plants like marijuana. Okay, THC, which is tetrahydrocannabinol, and some phenols are used as pH indicators, which we've used in the lab there. Phenolphthalein. Okay, acid-base indicators. Adrenaline is a phenol derivative and also a hormone. Okay, there's your phenol right there. Properties. Okay, unlike branched alcohols, phenol is a weak acid with a melting point of, and when we say acid, it's not an acid per se, you know, like hydrochloric acid, these kinds of things. An alcohol is an OH group. And what happens is when you put an OH group into water, that H kind of floats off sometimes. If the oxygen has a strong ability to steal the electrons, then that hydrogen off the alcohol group will jump into the water and make acid. All right, and branched alcohols, they are a stronger acid. They produce more hydrogen. But phenol, with the benzene around it there, tends to be a weak acid. All right, that hydrogen that's hanging off the oxygen there for the hydroxyl group of phenol, it tends not to jump off into solution. It tends to stay there. Okay, and the table below is a comparison of pH of phenol with the pH of water and acetic acid. Okay, so there's the pH of water, which is neutral. Acetic acid there has a good tang to it, right? So the pH is about 2.87. Phenol, yeah, it's in there about milk. And there's Sonia the cat. Get out of here. Go on. You haven't run away yet. All right. Properties and preparations of phenol. Oh, she didn't like that. She's walking away. Good. Phenols will react with a strong base like sodium hydroxide, but not with a weak base. So phenols are weak acids, and in order to get them to react, you need a strong base like sodium hydroxide. If you put a weak base in there, okay, a sodium bicarb or something like that, and it's not going to work, because you see, phenol isn't going to let this hydrogen go easily. All right, in order to get this hydrogen to react, you need a strong base that's going to rip this hydrogen apart, which happens here. Good. Alcohols do not react with sodium hydroxide or baking soda. Phenols are stronger acids than normal alcohols. So here I've got a branched chain alcohol plus sodium hydroxide, no reaction. But going back to the previous slide, these guys here will slightly react. Ethers. Getting back here to naming them. Ethers are these organic compounds that have the general formula ROR, where both R groups can be alkyl, which is chain, or aromatic. Okay, so just be careful when this is written like this. This could be an aliphatic chain And this side over here could be benzene, could be another chain. All right, and they're both single bonded to this oxygen. Naming ethers. Okay, common names of ethers list the alkyl group in the alphabetical order followed by the word ether. So this is the old school name here. We've got methyl and a methyl, and this is my ether group, so you go dimethyl ether. Okay. We'll use a prefix if both alkyl groups are the same. So dimethyl ether. Here I've got a methyl group. Here I've got an ethyl group. So you go ethyl methyl ether. Okay. That's the old school name. But this is where this is what I want you guys to know. Naming ethers with the IUPAC system. Okay. What we're looking for here is an alkoxy group. So an alkoxy group consists of an alkyl group and an oxygen atom. It is named by dropping the alkyl, the eel, okay, and adding oxy. Doesn't make any sense right now. We'll get there. So here we've got methoxy. This one here, let's call it ethoxy. This is only for ethers. So here, basically the key to naming an ether is you need oxy. Okay, look at this one. Phenoxy. Methoxy, ethoxy, phenoxy. So here's the key to naming an ether. Name the longest continuous carbon chain corresponding to the parent alkane. Name the remaining part as the alkoxy group. So let's have a look here. Here I've got this is obviously an ether. That's how you identify the functional group and then go after. So there's an ether. Okay, so ether means I'm going to have an oxy somewhere. And here I've got a methyl, and here I've got an ethyl. All right, so your longest chain will go last. All right, so here I have, because this one here is the shortest chain, I have methoxyethane. That's how you do these ones. Identify the functional group. Okay, ethane, I need an oxy. I have a short chain, a long chain. This is going to be my end. All right, so it'll be methoxyethane. More examples here. Have a look here. Okay, you're looking at this on a test day. Okay, okay, that's an that's an ether. Okay, where's my longest chain? I got 2 carbons here, 2 carbons here. Nada, ethoxyethane. Okay, have a look here. I've got a propyl group, and here I've got a butyl group. All right, so this would be propoxybutane. This one here, I wouldn't ask this on a test like this, but you see why this can get, we can spend a lot of time on this, but we're not going to. But you see here that this butane group is attached to the 1 carbon, right? To the oxygen. This oxygen here could be attached to the 2 carbon, which would make this 2-propoxybutane. But we're not going to get there. Be able to recognize something like this, okay, and recognize it out of a crowd. This is what we're looking for. Practice questions. Give the common IUPAC names for these guys here. You can have a look at those, okay. And here I have 1-ethoxypropane. Here I have ethoxybenzene. Now you're looking at this. Remember, your last, your big banana is always going to be last. In this case here, prop. So ethoxypropane. Here I got eth and I got a benzene, so ethoxybenzene. Properties and preparations of ethers. Going back to our original slide here, ethers there, they're bent like water. Okay. All right. And You remember how alcohols were bent like water? Remember that first slide there? This is slide 53. Let's go all the way back up here. Where is it? Right here. See how these guys are all bent like water? And yes, water will go into water. Funny enough. Okay. Alcohols will go into water. But only, I think, if you have 5 carbons or 6 carbons and then they start to not go into water, because this would be a non-polar carbon chain, which is going to keep it out of water. But as long as your carbon count is relatively low, 1, 2, 3, 4 carbons, it'll go readily into water. All right, but as the carbon count gets longer and longer, no, it ain't going to go into water. Even though this is crazy polar, as you increase the non-polar chain here, that'll start to trump this guy here. Ethers, you don't get, these guys here are different than alcohols, because the alcohols only have a carbon chain on one side and then you have this rinky-dink hydrogen here. Ethers, though, they have carbons on both sides of the oxygen. Now, oxygen is the big boss, but carbon isn't really a slouch. And in this case here, when you have one carbon trying to fight against the oxygen for these electrons, oxygen, nah, forget it, it's mine. But if you got one oxygen and a carbon on this side and a carbon on this side, oxygen is it's a little bit in trouble. It's still the big boss, but it's in trouble. And here you get hydrogen bonding, here you get hydrogen bonding, but slipping back now to 53, really no hydrogen bonding between ether molecules. You only get hydrogen bonding when you get an OH group. Okay, they have lower boiling points than alcohols with a similar molar mass. And I'm sorry if you can't see that. Pause the video and blow it up a little bit here, but you'll see there that the boiling points are considerably lower. Okay, higher boiling point than alkanes of the similar mass because of their polarity. They're still polar, but they're just not as much. Okay. And that is the end of the video. If you guys have any questions for me, please don't be afraid to email me. Keep working on your assignments. If you're having any issues, let me know. Assignment 3 has been posted. You got over 2 weeks to do this. I think 2.5 weeks there. So please consider this. This is exam time. Every question is a potential exam question, and you just might see them again. Okay guys, please be safe, take it easy, and we will see you soon.